You have fallen into Event Horizon with John Michael Godier. Jason Wright is a professor of astronomy and astrophysics at Penn State and a member of the Center for Exoplanets and Habitable Worlds. He studies stars, their atmospheres, their activity, and their planets, while also working on SETI. He is a project scientist for NEED, a PI of the Nexus for Exoplanets System Science, a co-PI of the Miniature Exoplanet Radial Velocity Array, and a member of the Habitable Zone Planet Finder team. You can learn more about his research on his blog, link in the description. Dr. Darryl Seligman completed his undergraduate degrees in mathematics and physics at UPenn in 2015 and his PhD at Yale University in astronomy in 2020. He was a T.C. Chamberlain Fellow at the University of Chicago Department of the Geophysical Sciences after completing his PhD.
Jason Wright and Darryl Seligman, welcome back to the program to both of you.
Thanks. It's good to be here again.
Thanks, John.
Now, gentlemen, we're getting back into the wonderful topic of the absolute variety of weird objects in the solar system, especially in regards to comets and asteroids and the in-between, where you have something that looks like an asteroid but acts like a comet and so on. And it's always been said that there's just a fine line in the distinction between an asteroid and a comet. But now we're starting to find that there are actually a lot of variations of the in-between. People talking about Manx comets and Damocloids and things like that. And before we get to dark comets, could you guys tell me what exactly is a Manx comet?
Jason, do you want me to answer that?
Yeah, why don't you jump in? You're the expert.
Yeah, so there's, like you said, John, there's this whole kind of continuum of activity between comets and asteroids. And just to back up a little bit, right, the comets are things very classically, you would define an asteroid as something that has no dust tail or is inactive, and presumably then, because there's no dust tail, has no icy volatile material, while a comet would be something that lights up with a cometary dust tail that, as ice sublimates, comes off the surface and small dust particles come with it and reflect sunlight. And so classically, those were two separate things. And like you said, there are a lot of things on the continuum between inactive and asteroids. So the Manx comets in particular, that term was coined by Karen Meach several years ago now. But those are, very broadly speaking, objects that look like, from their orbits, they look like they're comets. So they're on comet-like orbits coming from the very distant parts of the solar system where comets normally come from. But they have very little, if not any, dust production or activity. So they seem even, sometimes they even get close to the sun and they don't have anything. So it seems like there's no icy material in them. So one way to think of it is an asteroid-like thing on a comet-like orbit. And so it begs the question, how did you get all of this volatile, depleted material out into the outer solar system? Because if it had formed out there, it would have had ices.
I do like the term Manx comet that Karen Meach came up with. And as I recall, she's a Pan-STARRS, University of Hawaii. I've interviewed her before, as a matter of fact. But a Manx cat is a tailless cat. And now that we have a tailless comet. But it's on a cometary orbit, right? So it's basically indistinguishable from an outer solar system object like a comet on a very highly elliptical orbit, right?
That's correct. Yeah. So it looks like by its orbit, you would just guess that it was a comet. It just turns out that it doesn't have too much or any activity.
And as I understand it, we also have sort of the opposite, right? That we now have these asteroids that, if you look very hard or very deep, do seem to have a bit of activity in the sense that they'll get a weak coma or have a little bit of dust coming off them, right, Darryl?
Yeah, that's absolutely right as well. So there's the flip side of that is they've discovered very, very broad umbrella term is active asteroids, and there are subsets of those, but things like, you can call them, one example are main belt comets. And so it's something that's on an asteroid-like orbit where everything around it seems to be an asteroid, but it does, in fact, have faint cometary activity.
Now, with discovering these types of objects, we have an elephant in the room coming. And obviously, Pan-STARRS started the ball rolling and actually found in Oumuamua originally. But we also have the LSST Vera Rubin Observatory, and we're going to have these all-sky surveys where we could potentially expect, or actually we can expect, detections of comets and even interstellar objects on a much greater scale than we ever have before, and outer solar system objects, on all sorts of things. It's absolutely amazing. I'm very excited for this telescope, but also the possibility of using it to look for technosignatures. What's your view on that, Jason? You first.
Yeah, well, I mean, you talk about the elephant in the room. I mean, this all came about, I think, because when Oumuamua was first discovered, some of us on Twitter were joking that they should name it Rama after the alien spacecraft that visits the solar system in the sci-fi novel Rendezvous with Rama by Arthur Clarke. And a lot of the discovery of that comet tracks the novel, the opening chapter of the novel, although we pretty quickly established that although it had a lot of strange properties that we did not expect, it also had a lot of properties that are consistent with it being an interstellar comet and not an alien spacecraft or something. Of course, Avi Loeb really wouldn't let go of this idea and wrote a lot of papers that it might be a piece of a discarded light sail, a very thin object being pushed by radiation pressure. And so, Darryl and I have both thought a lot about this and why we understand that Oumuamua is not that. But it raises the question, if there were to be a lot of alien spacecraft drifting through the galaxy, or if one of them were just, passing through the solar system, would we be able to tell? Would we be able to tell if one of the things that we've cataloged as an asteroid that no one's ever looked at might be an alien spacecraft? And so even though Oumuamua itself, I think there's no reason to put it in the interesting for SETI category now, the experience has, I think, opened a lot of people's minds and gotten a lot of us thinking about exactly how would we establish that something is a real asteroid and not a spacecraft, or a comet and not a piece of a light sail.
Darryl, your view?
Yeah, no, I think I basically agree with everything Jason just said, that retrospectively, yeah, there is no obvious reason to think that Oumuamua was an alien spacecraft. It also, is no longer the whole argument that it could be artificial hinges on the combination, just like we were talking about, you've got these Manx comets, which have no activity but comet-like orbits, or main belt comets, which are asteroid-like orbits but activity. It all hinges on the orbit dynamically having a non-gravitational acceleration. So it's a comet-like acceleration now, but no associated dust coma. And that was, at the time, unique in the sense of having comet-like acceleration. Remember, inactive asteroids do experience non-gravitational accelerations. They're just much weaker. So it was very much unique. And I think some of what the conversation that was spurred was because that combination of non-gravitational acceleration and no dust coma was unique at the time, but we found a bunch of more objects like that. So it's no longer even a unique thing within the context of the solar system. But that does kind of now that we've found one of those objects, it does open up the possibility, or like Jason said, we can all be a little more open-minded about what we can expect to look for.
Yeah. So the non-gravitational acceleration, what we're talking about there is that we understand where all of the masses in the solar system are that can perturb orbits, all the planets and even the large asteroids. So when something's in orbit around the sun, we can project its position into the future for years or decades, depending on how well we can measure its position and velocity now. The exception is when something other than the force of gravity is pushing on these things. And there's a few of those. With comets, when you have the outgassing, that's like a rocket. And so that will perturb the orbit. And so comets do not stay on purely gravitational orbits. We see them, especially if they have a lot of outgassing, change their orbit because of this rocket effect. The suggestion that Avi had that Oumuamua was an alien spacecraft was in part based on the fact that it definitely did experience some kind of push other than due to gravity. And so his argument was that it was an extremely thin object, so it reflected a lot of sunlight, but it was something like a sail, perhaps less than a millimeter thick. And as a result, just the gentle pressure of sunlight against it was enough because its mass was so low that it was sunlight that was actually pushing it, not thrust. Now, something would have to be extremely low mass for something as gentle as sunlight to push it so dramatically. But we do actually see something like that for very small asteroids that sunlight hits them, they heat up, they re-radiate that sunlight away as heat. And over a long amount of time, if they're small enough, we can actually detect that very slow thrust that's generated by those photons, and that's called the Yarkovsky effect. So we have this neat interplay where we want to understand small asteroids. We want to understand their orbits. Part of that is planetary defense. We don't want them to hit us, so we need to know where they're going. We want to understand things that look like asteroids that have outgassing. And we'd like to find, if they're out there, probes, maybe there's a spacecraft and it's hollow, or maybe it has a light sail. And all of these things involve understanding the very small changes from a purely gravitational orbit that might be going on. And so it's neat that we're in this era with LSST coming online, and now we have, and all of these big surveys that have come before it, that we can go through and try and catalog them all and measure all of these and understand comets, understand small asteroids. And while we're at it, we can, I think in many cases, show that those things are not spacecraft. That really is a rock out there that's solid and it's not something hollow.
I think the big problem with Oumuamua ultimately is we didn't know at that time when that was of interest, we didn't know all of the different kinds of rocks that can happen in the solar system. And I mean, who knows what the universe is like? And there was all sorts of talk about shards of planets to sort of try to explain its geometry. But was there ever any sort of clarification on the geometry of that object? I mean, was it a pancake? Was it a big long shard? What do we think today was the actual shape of the object based on what little data we actually have?
My understanding is that the best fits to the light curve, the best description is that the axis ratio is about something like 6:6:1, so sort of pancake shaped. The original, there was a press release that had a picture, a drawing that someone had done as if it were 10:1:1, so cigar shaped. But I think a really fat pancake is more consistent with the data. Is that your understanding?
Yeah, some of the original papers, I remember, so you can go and look back and get the whole light curve of Oumuamua over 4-ish weeks, where it's only really good data for really high cadence data for the first week-ish. And so we put together like a full light curve. There was this Belton paper from 2018, and then the annual review, we put together the light curve, and you can see it kind of go from bright to dim. And so remember that a lot of the papers that quoted that tried to estimate the size from the light curve, and I should say, you see how the brightness changes, so it's going from bright to dim. That could be explained if the object was elongated, because it's just elongated and rotating or tumbling, so it's showing you head-on versus edge-on projections of reflected sunlight. That's why it's getting brighter and dimmer. As the first couple of days after the discovery, everybody was trying to get observations of the object, and you have to capture the full light curve. You have the bright to dim, so the full phase of the light curve to get the shape estimate. So the first several papers written about Oumuamua that were publishing new data, like published as quickly as possible, they got one night of data, something like that. Most of them didn't get full light curves. So you'll see estimates that were varying from 10:1 to 6:1 to 4:1 to 4 to 3:1. So all these different estimates. And just because we were working with limited information, right? And then there's also the subtle effect of the phase angles. So the angle between the Earth, the sun, and the object also changes how drastic that brightness change will be. But then after we were able to get all of the light curve, it was about 2 years later that there's this paper from 2019 by Mashenko, who essentially went back and fit every possible shape to the entire, under the action of tumbling and even rotational forces and stuff like that, to figure out exactly what thing would fit the light curve best. And it turned out that there's a greater than 95% confidence that it was exactly what Jason said, it was a 6:6:1 shape, as opposed to certainly not the 10:1 shape, but also not the cigar shape that was kind of everybody assumed was the shape of the object because of that press release image. And that was because of that, that's what people thought. And the reason is just because it's very unlikely for a cigar shaped thing to get very dim every single time it gets dim. Whereas, because it always has to, the kind of short axis always has to face right at you to get the very deep minima. Whereas a pancake just has to complete an entire rotation to show you its short axis.
Ah, see, that clarifies that, because I remember during the early days in the paper, when everybody was looking at trying to figure out what the geometry was, the one that looked the most like what we might have in the solar system was the pancake. You could imagine the solar system having a pancake-shaped object in it. So that was the one I was wondering. I wonder if they can prove that that's the geometry, because that makes the object less weird, right?
Yeah, I mean, the 6-to-1 shape is still pretty extreme. That's still more extreme than most things that we've seen. But it is still weird. But yeah, the pancake shape is potentially a more natural outcome of processes that we think that planetesimals form by. And John, also, if you remind me, I can send you, there's Aster Taylor, who we have some episodes recorded with, has this paper that we have an online published video of the tumbling best fit shape as it fits to the light curve. So I can send you that. It's like published in the in-print paper, it's just images, but the video is published online.
Yeah.
Excellent. Please do. Now, Jason, can you envision a technosignature within the solar system that the LSST could pick up that functions in the same ways like an Arnold louver or something like that? In other words, say you have a small group of artificial objects moving in a very strange way, they're arranged in a rosette or something like that, that just isn't going to look like nature. Is that a technosignature, or would that fall apart over time?
No, that's interesting. I haven't thought about that before, that you might see them flying in formation, essentially. So what we're talking about now is things orbiting the sun, essentially, like spacecraft, not things on the surfaces of planets. And, what would the giveaway be? So one thing you have to ask is, are these things derelict? Are they just flying around without any thrust, or are they active? Are they maintaining their attitude control, or are they tumbling and spinning? Asteroids are typically tumbling, spinning, and asteroids typically don't do anything that gravity doesn't make them do, except, as we've talked about, these non-gravitational accelerations. An active spacecraft might be distinct because we don't see it rotating at all. And of course, it might decide to change its orbit. It might be just cruising along and then suddenly decide it wants to be somewhere else in the solar system and accelerate away. So those problems, are all possible things that could be technosignatures. They also might have unusual reflectance. So rocks are kind of gray, but the subtleties in exactly what shade of gray in the optical and infrared wavelengths help us understand the surface composition and what kind of asteroid or comet we're looking at. Of course, there's no reason a spacecraft should have that same set of colors. And so that's another way that we might look at something and say, hey, that's odd. Let's get a better look at it. They presumably are not solid objects like solid rock. Presumably, almost all of the spacecraft we build, even the ones that don't have people in them, but just ordinary spacecraft, have big solar panels or other things that mean that the cross section they have to reflect light is much greater than an asteroid of the same mass. So the density that you infer from seeing this big cross section compared to the mass of it of our spacecraft is all pretty low, and it's remarkably consistent. I was working this out, and New Horizons and the International Space Station and typical communication satellites, they all kind of have similar area to mass ratios. And in all cases, photon pressure from the sun is probably detectable and will make them look a lot like comets, or at least maybe not the most active comets, but low activity comets, as if they had that thrust. So for all of these things, I think there's an opportunity for looking for them. Now, you suggested that they might be formation flying, which that's kind of neat. I hadn't thought about that, but one could certainly look for, asteroids, things that get cataloged that have nearly identical orbital parameters and are essentially keeping station with each other. That would be kind of cool. It's not obvious to me that would have popped out in a catalog so forth, that anyone would have noticed.
Yeah, I mean, that could also be like a recent disintegration event, right?
Yeah.
So you have to do
It could. And so, well, right. But that's really interesting, right? Do we see those? I don't know.
Yeah, you do see those, and you can kind of in fact, I think you take objects and try to trace them back in time by doing these kind of forward models of how you run it through a computer and see how their motion evolves in time, and you'll see that
Yeah.
the more recent disintegration events that happen, the closer their orbits are today. You kind
Yeah.
of spread
Or
out
you could run them backwards and say they all have a common point of origin.
something. Yes, exactly.
Yeah.
So those types of things they do kind of look for, but I agree that I mean, they already know how to kind of search for that. So if there's something that's suspiciously
Yeah.
close together, that would be an interesting,
Yeah.
interesting if it's a technosignature or not.
Right. In all of these cases, we can probably think of some natural explanation that would do it, but those things are necessarily going to be rare and interesting and worth studying. One thing that a spacecraft could do that would be very challenging to notice is imagine it just took like a right angle turn. It just completely decided to thrust, and it didn't do a nice slow orbital burn. It just fired away for half an hour and totally changed its orbit. It would be very difficult to notice that this had happened because it would be on such a new and distinct orbit. It would look like a brand new object we'd never seen before. So there would be some object that we had been tracking that we just lost and just for some reason couldn't find again. And shortly after we lost it, we'd pick up a brand new object on another orbit. And if it was sufficiently different, I don't think anyone would put two and two together. And so it's an interesting problem, I think, still unsolved in the astronomy community.
Yes, certainly still not solved, right?
My guess is this has been solved in the intelligence community with respect to spy satellites and things like that. So I bet the math has been worked out, but not by us astronomers, about how you would tell that, say, these two objects have very different orbits, but in some space, in some way, you track one back in time, the other forward in time, and look, they were in the same place at the same time. That's when the thrust happened. So it's a neat puzzle.
It is, and it was just something I was thinking about last night. Just having coffee. And I was thinking, I wonder if you could see something weird happening out there. And yeah, something doing a turn might do it, but I don't know. The thing is that things have disappeared in astronomy where they'll observe something and they don't see it again for 25 years, and then there it eventually is again. So that is not unheard of, that you lose track of known objects. Yeah, even comets, actually. It already used to be that way.
Well, that's what's so neat about this new era of large sky surveys like LSST, but also Pan-STARRS and these others, is that we don't ever have to lose them again, because by surveying the entire southern sky every 3 days, we should keep picking them up. So only the very faintest, smallest objects. So, I mean, if it's so small that you only see it when it's near Earth, then yes, once it's gone, we might completely lose it. But above a certain size threshold, we should, rediscover all of the lost asteroids out there and never lose them again as long as we keep these sky surveys going. And then, right, it'll just be these little ones. You have to wait.
Yeah, and just to like kind of clarify that point, right? So John, you were saying that you'll lose, it's kind of routine in astronomy that we lose signals from things. But as Jason is saying, that always happens at the detection limit. So as faint as you can go. So, right, some of these very small near Earth objects, it's tough to see them because, they're both very small, and then their orbits, even though they get close to the Earth, their orbits aren't aligned with that of the Earth. So they don't get close to the Earth every time the Earth goes around. It has to happen. It has to be every couple of years until they get close sometimes. So it's actually, if you just look at the trajectories of the objects through time, you can predict when you'll lose them or when not. So it's not like in all throughout astronomy, we're just losing things and we have no idea where they went. So sometimes it's, we know that this thing is going to get so faint that no telescope of ours is ever going to be able to see it. So with LSST, like Jason is saying, we'll be able to find a lot. We'll be able to rediscover and find a lot of lost things and a lot of new things that we knew we were going to lose. But then they will still push us to lower, like there are probably much smaller objects that LSST is going to find, maybe even at the meter scale or something like that for near Earth objects. And then again, you'd expect to lose those. So you can kind of quantify the fact that there are objects that you would lose, that you would expect to lose, versus objects that you lose that you don't expect to lose, because if it kept going on its trajectory and it's about as bright as it was when you lost it, you should still see it. So there is a distinction there.
Do you think that, as we get a data set with LSST and stuff starts appearing, would it be possible to go back through archival data sets, just plates, photographic plates, sky surveys from the past, and try to find objects that we spot now that are new to us and see them in the archive now that we know where to look. And I'll direct that to you, Darryl, because you probably know more about that than we do.
Yeah, I mean, so that's a fantastic idea, John. And in some sense, they already do that. I mean, maybe not always going back to very oldest archival things like observations from decades and decades ago, but there is, for the small bodies at least, so anything that is a small body that's moving transient in the sky, in the solar system, what happens is every night the data of any new observations get reported to the Minor Planet Center, and then I mean, they do these with a bunch of supercomputers, so it's not like we just sit there and try to link things up ourselves, but they will take every new observation and try to link it to objects that they already know about and say, does this new object, now that we've detected it in tonight and the last couple of nights, and we know how it's moving and what its orbit is right now, is that the same object as an object in the past? So in some sense, they're already doing that. One thing that's going to be a big challenge is with LSST, there are going to be so many more detections per night that they have to scale all of that up for the larger volume of just nightly detections. But another issue, I mean, me and Jason just are on this paper that just came out that Astor Taylor led. But one issue, though, is that when you retroactively go back and you see a new object and you go back and try to link it up to everything that's done before, if it has accelerated in that time, non-gravitationally, then it's not clear that we'll be able to link it up successfully. So I think that's another kind of interesting point, is that it's possible that you lose objects just that because they're accelerating non-gravitationally.
Now, Jason, that question actually it was inspired by Tabby's star, because you remember everybody was going back through the plates and seeing if they could get a brightness on this thing in the past. Is there, and everybody's going to ask me, is there any new information on Tabby's star or is observation still ongoing, or, what's going on with it?
Yeah, I mean, it's still being monitored and it still occasionally gets dimmer. I think what we're all waiting for is for the James Webb Space Telescope to make a very accurate and precise measurement of the mid-infrared flux, because the dust that is blocking the light from Tabby's star, it should not be able to hide from JWST. I mean, it's got to be warm, and JWST has the sensitivity to detect it. And once we detect it, we'll have a better sense of its orbital distance or if it's orbiting the star at all and not something intervening or something like that, some dust cloud. But it's very challenging. To make a very precise measurement with JWST is what it was designed for. But to make a very accurate measurement, to know that we're seeing more mid-infrared than we should for that kind of star, is a real bear of a calibration challenge. And so I don't know how long that's going to take to be confident that we know the calibration of those instruments well enough to make that measurement. But I'm looking forward to it, because I think most of us are expecting the dust to be in orbit around the star. But if we can't find it, then I think we need to go back to the drawing board about where the dust is. And perhaps it really is an intervening cloud of some sort, which I think would be really interesting. It's a dark horse favorite candidate of mine. I don't think that'll be the answer, but I like to keep it in mind.
I actually, about that dark horse, there was also work recently, another paper that came out about HD 139. You remember that was the repeating weird thing from the Kepler data where it looked like planets moving past, but they weren't periodic. There was no periodicity. And I know that periodicity is a problem with the random transitor. And then they looked again recently, it's gone. And so I'm thinking to myself, what is in the interstellar medium?
Mm-hmm.
Like rogue planets, and things like that, that might, a cluster of rogue planets. And that's actually been seen before. That's actually the candidate, if this was the case, it's a candidate for the most distant exoplanets ever seen, because they were in a quasar,
right.
Gravitationally lensed quasar. You remember that, a cloud of planets?
Yeah.
Well, anyway, what's in the interstellar medium? Because we know things like Oumuamua get ejected out of their star systems, and even planets get thrown out there. And I wonder if that was the case for that, or in Tabby star's case, or we should call it Boyajian star. dust in the interstellar medium, cold dust. Though I do admit, I do still like the original hypothesis, which you might have been an author in the paper that Dr. Boyajian put out, that cold comets in a collisional model. I haven't left that off the table yet. What do you think?
Yeah. So a rogue planet out in the interstellar medium, just floating around, going in front of a star, could in principle make the star briefly dimmer. It also in principle could do a slight lensing and make it briefly brighter. And it all depends on the geometry of that. But it's not going to create these kinds of effects that we were talking about, and they're going to be super rare. The dark horse candidate I have for what would have to be causing Tabby's star, if it's not circumstellar material, you would need something to hold the dust together, like a star, but it can't be luminous or we would see it. We do know that there should be free-floating black holes, stellar mass black holes from supernova explosions all through the galaxy. And we know many of them should still have some of their circumstellar material. Now, for a while, they feed on that material and they're quite bright. But once they're done feeding, there's still some material left over that will get extremely cold. This has never been observed because there's no way to observe it. It's just extremely cold dust in orbit around a black hole you cannot see. There's no way to tell it's there. But it has occurred to me that that they should be able to be seen in silhouette. And it should be hard. It should rarely happen that they come between us and a distant star. But I wonder if the Roman Space Telescope, staring at the bulge of the galaxy, won't see a few of these things occult background stars. And I wonder if it wouldn't look a lot like Tabby's star. It's again, a dark horse candidate of mine, something someone should work the numbers out on. You try to work the numbers out, it doesn't look great, probably not what's happening. It's something I've been thinking about. Now, as for the random transitor 139139, we're actually working on that here in my lab. I have an undergraduate student who's analyzing those data very carefully, because I think the reason it doesn't get a lot of attention is that most people who take a look at it think that it's probably an electronics glitch with the Kepler spacecraft. There's a rare effect that certain CCD pixels can have that might be able to explain it. But it's very tricky to see if that's what's going on for some technical reasons. And so I have an undergraduate taking a very close look. And my hope is that we will be able, by the end of the year, to definitively say this pixel on the camera was acting up and that's why the random transitor did what it did. Or say, no, we are confident that the dimming that the star underwent was due to the star itself.
I am looking forward to that paper.
Me too.
Because it definitely puzzled me, that one. And I know you have a hard out soon, so I want to ask you a few more questions. And then, Darryl, I have dark comet business with you after that. But yeah, now Shilsky star.
Yeah.
Jason, I know we both rather like that star. Very peculiar for many reasons. Has anybody decided to take another look at that thing and see if there are transuranics in that star? What's going on?
So there's a group in Europe, and I'm totally blanking on the names of the astronomers involved. But when I was visiting Uppsala University, I spoke with one of the team members, and they have high resolution spectra of the star at infrared wavelengths. And the nice thing about going to the infrared in a case like this is that for technical reasons, there are fewer absorption lines that a typical atom or ion has at longer wavelengths than shorter wavelengths in this case, which means that the spectrum is simpler out there. The biggest challenge with Shilsky's star is that it has so many absorption features from so many ions and atoms that have extremely complicated electronic structure that all the lines overlap. And so normally we would see the chemical fingerprint and recognize it. But there's so many fingerprints of so many different species that are much stronger than they typically are in that star that it's hard to make any confident line identifications. So by going to the near infrared, they have a simpler spectrum with fewer overlapping features, and they've been able to make some progress. So I sort of pestered them about this, and they've worked entirely from the principle that all of the elements involved are long-term stable, which is a perfectly reasonable assumption to make. And based on that assumption, they have some very good models for the star and seem to have explained it well. But what they haven't done that I'm asking, I bug them to do, is to show that there is no need for short-lived isotopes in the spectrum. And that's always been the puzzle, that some of the strongest lines, the best identified lines, seem to come from species with very short half-lives that just cannot exist in the atmosphere of a star. And so I've asked them if they might take a look and just entertain the hypothesis that those are there and, do we need the hypothesis? And in fact, could we rule it out? But based on how well they're doing modeling the spectrum, my guess is that the puzzle has more or less been solved, even if that particular question of short-lived isotopes has not actually been addressed.
Be interesting to see that. Now, of course, there was always the question about what, when you're looking at transuranics in a spectrum, that's, messy because it's not so well known.
Well, right. We don't actually know what the line strengths and positions are. We have to rely on theoretical models of these atoms, and they aren't precise enough to make firm predictions. And so, you're on uncertain ground.
Now, with the LSST, Vera Rubin, that seems like it, with the cadence that's going to do all sky surveys, that seems like it's almost a lot like Kepler. Do you expect more exoplanet data and weird transits like Tabby star to show up? Do you think it's really has that capability as well as spotting solar system objects?
It'll definitely help a lot with exoplanetary astrophysics. It's not designed to find lots of new transiting planets. The cadence, it will revisit a star perhaps once every, say, 3 days or something like that, whereas these spacecraft like TESS and Kepler that found so many would revisit the star and take another image every few seconds. So while it will stare for the same sort of 5 years at the sky that Kepler did, making a one measurement every 3 days versus making a measurement every few seconds is just, it's such a world of difference that we don't expect a lot of planets to be discovered. Now, that said, it will be a lot of data, and it will make some transiting planet discoveries, I'm sure. A system like Tabby star is actually well suited for it because those variations kind of happen on the timescale of days. And so we'll see things jumping around. And if we find something like that that's getting unexpectedly dimmer and brighter, then we can go and follow up with higher time cadence and, and track those. So hopefully we'll find some more. There are all sky surveys like the Assassin survey that keep finding these wacky stars. They call them dipper stars. In virtually every case, it's a young star with a disk of some sort, like a warped disk of material. And as the disk rotates and it's warped, and so it's not always the same geometry, it will occasionally block certain parts of the star's light. And you can get these very dramatic changes in brightness that are very reminiscent of Tabby's star. But so far, all of the systems have been obviously young systems where we understand why they're dipping, or very faint, very distant objects where I'm not really sure what we could do to study them. What was so great about Tabby star is it's so bright and close. We could really, really go to town on it with follow-up.
Not that close. I think it was 1,500 light years, something like that.
Jason, have you done that kind of calculation yet? The mapping out like how many Tabby stars you would be detectable with LSST?
So interesting question. The challenge there is the cadence. How often do you need to observe the star to tell? And then, what is the phenomenon that you're after? I mean, there were so many different timescales with Tabby star. It happened, over the span of a few months. And, there do seem to be vaguely episodic regions where times when it gets a little bit dimmer and, they happen in clusters. It's very hard to characterize. But no, I don't really know the answer. One of the challenges is that a star like Tabby star is so bright, which makes it great to study. But LSST is the Ruben Observatory is so sensitive that a star that bright actually saturates it. And so we will only find fainter stars with LSST undergoing this because it's designed to find the very faintest objects, and the brightest objects just blind it.
That's very good for solar system objects, though. Especially if you're looking at objects in the Oort cloud, just objects floating around there. Like, I forget what the designation of it was, but it was, we were there with the
Horizons?
The probe, New Horizons, and we saw that, one of those objects, but there has to be a ton of those out there that we don't know about yet, and even entire minor planets.
Oh, absolutely. There was a huge effort to find that object. Akaroth, is that what it's called, Darryl?
Arakoth.
That's right.
Arakoth. They searched for years to try and find that because they knew there should be so many of them that there would be one that they could aim at. But they're so faint and hard to find that it took years of using the biggest telescopes in the world to track just one of them down. And in the end, they needed the Hubble Space Telescope to search a big region of the sky to try and find that. And they found it in the nick of time. Bringing it full circle, I think one of the real surprises of that object is that it's pancake shaped. And people, right, is that and this wasn't really super obvious at first, because as you buzz by it, it's hard to tell the shape. But I think the conclusion was nothing like Oumuamua's, 6 to 6 to 1. I think it's more like 3 to 3 to 1 or something.
Yeah, and it's two pancakes.
It's two pancakes. They're much fatter than Oumuamua, and they're stuck together. But the fact that it's basically a pancake, I think, is interesting. And maybe that's normal for things that are effectively in interstellar space. Because once you're out beyond Pluto, you're effectively in interstellar space, even if you happen to be orbiting the sun.
Right, and and it's not even the being in interstellar space, which is, Jason, the main takeaway for me. I think it's that, and there's some theoretical work that's been published since Oumuamua that kind of looked at this, but there's this process called the streaming instability, which is kind of one of the leading hypotheses for how these 10 to hundreds of scales and hundreds of meters scale planetesimals form, or even bigger than that. But maybe the natural outcome, the streaming instability, it's like you have gas and dust in the protostellar disk, and the gas and dust collapses into a cloud that is spinning and has a lot of angular momentum, and it eventually collapses. And it might be the case that just these planetesimals that form a natural shape for them is pancake-like, if not 6 to 1, but slightly elongated. And the Arakoth object was pretty clearly an object that was a binary, both of which were pancake-shaped, that evolved from, they exhibit tidal forces on each other that push them together. So one of the mental models I had, Darryl, for how Oumuamua got its shape is the bar of soap in the shower. That, you can get a novelty soap of any shape you like, but the more you use it, right, the smoother it gets. And as you erode it away using that soap, it'll always end up being the same pancake shape in the end, right? You get that really thin last bit of soap. And that's just what happens to any shape that you erode evenly in all directions. And so that's why I wonder, is that what's going on out here? Is that everything's out there just erode away, and so they all end up being pancakes? I'm glad you think of that analogy, because I thought it was clever when I came up with it, but I guess it has stuck. But the bar of soap thing, it also is one point about that, right, is that it and John, I have an animation of that I can send you for Oumuamua specifically, what that shape evolution should look like over time. That was for the case if it was made of pure hydrogen and it was just shedding hydrogen as it moved through the solar system. But it does help if it's kind of pancake shaped a little bit to begin with. Maybe even if you took something that was pancake shaped like Arakoth, or one of the lobes of Arakoth, and you subject it to isotropic-ish or even-ish mass loss, whether it's ice or being bombarded particles in the interstellar medium or whatever, you will create a more dramatic pancake-like sliver.
Yeah, Darryl, I remember years ago, I think the first time that we talked, we were talking about the bar of soap. Which that was years ago now.
And I guess Jason remembered it too, so that's pretty cool.
When we were writing the rebuttal to Avi back in 2021, we were trying to come up with this analogy with Sean Raymond. And so it's possible that it made its way, through Sean to me or something. But I thought that we'd sort of independently done that back in 2021.
Oh, no, I think, Steve Desch started using it when he did the nitrogen thing after the hydrogen. I just don't think
okay, I got it through Steve.
He came up with that.
That's how. Okay, I got it through Steve. That's how I first heard it. Okay.
That's also one of those things that a bunch of scientists could independently hit on, because it's the best example of what you mean, that weathering from all sides.
Right.
Jason, I believe you have a hard out in 3 minutes and you got a flight to catch, right?
Yeah, it's coming up.
So I will go ahead and let you go. And Darryl, I have more questions about weird pancake objects coalescing in the outer solar system. And we will be back in just a minute with Darryl Seligman. And we're back with Dr. Darryl Seligman. Now, Darryl, dark comets, and that's your specialty. When you look at outer solar system objects like we were talking about, and you get these weird geometries, and where you've got a binary system that coalesces just slowly, just sort of until they touch, they just spiral in until they touch, resulting in really weird geometries, overall geometries. And in this case, two pancakes with the New Horizons target probe. So what can we expect with dark comets from this sort of thing? I mean, could you have a binary dark comet that does this, that doesn't look like a potato, but two potatoes stuck together?
Well, in theory, I mean, you could have that with any of the small bodies. I mean, we know surprisingly little about the shapes of most small bodies that we've detected because we don't have that much follow-up data on them. Like Jason said, it was not obvious at first with the observations that they got that Arrokoth was going to look the way it did. And as a general rule of thumb, the smaller things get, the weirder their shapes tend to be, because when you get really large, like a planet, there's so much mass and gravity that you're roughly spherical. And as you get smaller, you get weirder shapes. And then it's starting to look like the more that we look closely at different populations of small bodies throughout the solar system and all different reservoirs of small bodies in different regions of the solar system, it turns out that a lot of things are binaries. So do come in pairs, and that could be just a very natural outcome of planet formation. So yeah, it's totally possible that you could have some of these weird small objects being binaries, and then some for reasons that have nothing to do with the fact that they're dark comets, just that they're accelerating, just the fact that they are small bodies, some of them could be binaries even. That's totally plausible. The one thing that's exciting, though, is, I mean, there's one dark comet. I know we talked about it before on the show, but 1998 KY26 is already the target for the extended JAXA Hayabusa 2 mission. So you're going to get, in 2031, we're getting up close and potentially at least rendezvousing, if not impacting or landing on the object. So we're going to have great images of what that object looks like. But because it's such a weird and important object and now a mission target, we had very good shape models of it from years ago. And so we know that object shape very well. And we have those from radar measurements, actually, which can get you very fine shape estimates for these small bodies. So at least that object, we know its shape and it's roughly spherical. So that one, it's 15 meters-ish in radius. That is a roughly spherical object. So we know that, at least, for one of the dark comets.
Now, Darryl, it just occurred to me that we have another elephant in the room, or an asteroid in the room. the soap bar. So let's say you get these two coalesced objects, the two pancakes stuck together into this weird configuration, and then you throw that to the interstellar medium with the effect of the soap bar. And after so much time, that's going to result in a really weird object geometrically. Do you expect the moment we turn on the LSST that we will see a population of like objects to Oumuamua in these wildly different shapes because of those situational, things that can happen that might result in some weird geometries?
So probably not. And there's a subtle reason for that. So my bar of soap analogy that we came up with for that hydrogen iceberg paper back in 2020, the reason it works so well for Oumuamua is like, yes, if you isotropically remove or uniformly remove stuff off the surface of a body, you'll make that shape just like a bar of soap. But it worked really, really efficiently for that theory that Oumuamua was made of solid hydrogen, because it's really, really easy to remove hydrogen off of the surface of something because it's so easy to turn it from an ice into a gas if it's an ice in the first place. So that bar of soap thing is really, really efficient for a hydrogen iceberg. The problem is, as you get to less volatile ices, which means ices where it's harder to sublimate them, it just doesn't work as well. And the idea for Oumuamua was that it was traveling in the interstellar medium, so it was being exposed to all of these like high energy photons, which you don't have in the inner solar system. And then as it traveled through the solar system, it was getting exposed to the sun's photons, and those were removing hydrogen off of the surface. But once you even get to something like water ice, that sitting in the interstellar medium, you're not going to remove water ice off of the surface. So you don't see this. That's why not everything is like a bar of soap, right? You don't see everything looking funny because it just doesn't that process isn't typically operating. And there's one area that we got inspiration for that whole model for Oumuamua's shape was it came from these people who were working on the shapes of some asteroids that were elongated. And the idea was that potentially as you travel through distant parts of the solar system or dust places where there's a lot of dust, and that would also occur in the interstellar medium, you'd get sandblasted. So fast dust hitting the surface will very slowly also do the same thing and remove stuff off the surface kind of isotropically or uniformly. It's just way less efficient. So that was the beauty of the hydrogen iceberg theory. It's not just that kind of bar of soap thing can happen generally, it's that it works really, really well in galactic timescales for Oumuamua. So I don't expect that you would see that everywhere.
Well, if you think about it, that's some interesting physics. So say you have such a hydrogen iceberg, and it goes through a protoplanetary disk and just is subject to that massive erosion of dust, as relatively speaking, and comes out the other side. That would be interesting. Just from a physics point of view, that would be an interesting thing to see. What do you think about that?
Yeah, absolutely. That would be interesting. I mean, and the extent to which it occurs, you could take it a step further, right, John, and say the extent to which it's occurring. I mean, if in the end you turned on LSST or something and you saw a bunch of strange objects and there was a whole variety of different shapes, maybe it can tell you, you could back it out and tell you something about the extent to which processes like that have been occurring and how efficient they are.
I think that's going to be a pretty amazing area of research as LSST comes online and we start spotting interstellar objects, to start building missions to go and look at them and see what the immense variety of possible things that can happen, because there's a lot of things that can physically happen in with objects traveling through different star systems, and where did they originate, and things like questions like that I think that's going to be, in 50 years, that's going to be some amazing science. I think very fruitful science.
Absolutely. Yeah, totally. And then I think you're just totally, we're on the same wavelength, John, because one thing is there's also a reason to think that those interstellar objects like Oumuamua and then Borisov, that they were ejected very, very early in their protoplanetary disks and the planet formation process. Whereas the things that are left over in the solar system, like the asteroids and comets, remember, those are the things that have been around for a very, very long time, much longer. They stayed in their planetary system much longer than Oumuamua and Borisov. So it is even possible to take what you said one step further, that's interstellar objects like Oumuamua could tell you more about what the primordial or what the original geometries of these things really are.
I hadn't thought of that, but that's amazing. I wasn't aware that it's thought that these objects, Borisov and Oumuamua, were ejected very early from their star systems, because that actually makes Borisov more interesting, because it would be really interesting to look at a comet that left its star system unmolested and see what kind of organic, whatever is there. And then we start again with our comets. This plays into that, is that how do star systems get their water?
Right.
Oh, wow. That gave me chills.
And exactly what you're saying. I mean, this idea of, so one major reason to study comets is, how do the terrestrial planets get water? But one important thing that is one of the major goals of cometary science, in my opinion, is to understand how comets get processed and how they evolve and how they eventually die. We broadly call it cometary fading. And one thing about Borisov that was really interesting is that it was extremely enriched in carbon monoxide compared to how much water it had. So it had much more carbon monoxide in it than water, which is almost unheard of in the solar system comets. And that's one reason that we know that it must have been ejected really early, because that carbon monoxide is a lot easier to remove via exposure to sunlight than water. So if it was sitting around its star for a long time, all of that carbon monoxide should have been gone. So its composition itself was telling you that it probably got ejected early. And then to take that a step further, those dark comets, it's possible, we don't know, right? The dark comets are still a total mystery, but it's possible that via our studying comets, we're trying to understand the evolution of comets throughout the solar system through time as they evolve and they get processed, that these dark comets, maybe these are just kind of the end state of comets. And these are what comets look like when they're kind of sputtering out, but still a little bit active, or maybe still have a little bit of ice left to go. Yeah, I think that's totally in the realm of feasibility, at least.
Interesting thought. Again, I'm physics. So, say you've got a comet that's almost done, but deep down it's got some volatiles left, and it gets hit by a meteorite that exposes them, and it goes bright again. Do you think that's viable to actually happen? In other words, a dark comet suddenly goes bright out of nowhere.
Yeah, that's totally viable. And in fact, John, that kind of thing has happened before. So there are objects like Bennu and Phaethon. Phaethon's going to be the target for Destiny Plus, Jax's mission. Bennu was already visited, and they kind of have dust activity, but sometimes, it's different cases. But basically, with Bennu, when the spacecraft got up close to it, they saw some dust coming off of it, but with no outgassing of volatiles. And there was just a little bit of dust you wouldn't have seen from the ground. And they think they're still kind of not sure about exactly what caused it. But one possibility is that micrometeorite hitting it like kind of exposes some stuff and sends some stuff flying off of it. There's other ideas like it's spinning up or something like that and spits off some particles, or there's kind of weird thermal effects where you heat it up unevenly and it causes fractures, stuff like that. But those things certainly are happening on all of the small bodies, and certainly we don't understand them very well, but it's entirely possible that these dark comets could be accelerating due to some entirely different mechanism, like the one you were just spitballing off your head. And that could also, cause them to go bright again or something like that. That's totally possible.
Yeah, that's interesting, because if you look at normal comets, we don't know how bright they're usually going to be. That's notoriously difficult to predict, because sometimes you say, well, we have this comet coming in and it could get, magnitude -1 or something like that, or it doesn't. And then you can get comets that you didn't really expect to be so bright, and that yet they are.
That's
and
right.
I actually remember observing one with Hale Bob back many years ago, and it really got bright, and then they do weird things, like they form their secondary tails and they do all sorts of strange things. And that's what led me to, ask the question is, what happens if something gets hit? The dark comet gets hit,
right?
Or it gets gardened, just like the moon, the lunar gardening, or it gets gardened, and then all of a sudden, this
Absolutely.
billions of years old object that should be dead, suddenly a little piece of ice gets exposed, and there it goes, accelerating. I think the take home, though, is I don't think enough thought has been put into things like Oumuamua to really go too far with it, just simply because there is just so much we don't know. But I do thank that object for stimulating a huge amount of thought. Even the alien option, just stimulating a huge amount of thought. And I think we're going to have a whole lot more of that with the LSST. But what if we don't? What if all we see for the next 20 years with what the Vera Rubin Observatory is more Borisovs and not a single other Oumuamua? Where do we go then?
And you're asking me specifically about just interstellar objects, right? And we're forgetting about the fact that we have dark comets in the solar system.
We're going to set that aside. Although you could end up with a dark comet from another star system as an interstellar object, but that's another discussion.
Right. You're just asking if you discover no more Oumuamua-like interstellar objects.
Yeah, it's not part of a like population.
And you're asking me what would the conclusion of that be?
Well, yeah, what would the result of it be? I mean, it would almost become like a wow signal, in a way, which the wow signal is not so interesting anymore, but it took 50 years before we figured out a viable natural solution for it.
Well, I think the interpretation of that would be just like purely scientifically, the interpretation of finding no more Oumuamuas with Oumuamua-like interstellar objects with Vera Rubin would be that we were extraordinarily lucky to find it, which means that it's something like a 3 to 5 sigma outlier event that we found it. So it was like a total fluke that we found it, because it would imply that there's, basically what we're saying right now to say the whole prediction that you're going to find more of them with Vera Rubin is based on the fact that we discovered these objects because if we say that we were not lucky, then that implies that there's about one Oumuamua-like object traveling through the inner solar system at any given time, which translates to about 10 to the 26 of them in the galaxy, or about an Earth mass per star. But if we don't find any more with Vera Rubin, then that would mean that, in fact, it must have been a very, very, very rare event that we would have found it. We got really lucky, and that means that the spatial number density of the Oumuamua-like objects is a lot lower than we would have thought if the Oumuamua was just a typical discovery with pan-stars. So then taking that one step further, that would then, the main issue with the idea that, for example, that Oumuamua was the chunk of a nitrogen glacier on the surface of an exo-Pluto-like object. The issue with that is something that we've published papers on, is that there's not really enough nitrogen that gets formed in protoplanetary disks. There's not really enough to fill the galaxy with that much material, about an Earth mass per star, in terms of nitrogen icebergs. But if it was a 5 sigma detection, so if it was if there were orders of magnitude less of them than we thought based on Oumuamua, then I think that would tell you that it was probably something like that.
Interesting. Now, the hydrogen iceberg idea didn't suffer from that, because that originates in a star-forming region, and there have been a lot of those in this galaxy.
Yes, that's right. So, there was plenty of hydrogen to go around.
Yeah, no shortage of hydrogen in this universe. Now, dark comets and acceleration. So, your recent paper with Jason actually gets into that these objects, these dark comets, can perhaps see the same sorts of acceleration that Oumuamua-like objects seem to see. Go into that.
You mean what would potentially happen if objects like dark comets were accelerated strongly?
Yeah. What about accelerations from them? I mean, could they, if we see them and we look at them and they accelerate, there's a mechanism there, right, that could potentially serve to explain Oumuamua and show us that we need to look for more accelerations in objects in the solar system.
Right, entirely. And I think, John, we had talked about this on a previous episode, that we kind of both agreed that these dark comets, they're different than Oumuamua, but they serve to contextualize it. And even though they're not exactly the same, they do show you that the non-gravitational accelerations that are kind of strong, maybe not as strong as Oumuamua, but stronger, like comet-like accelerations without a dust coma, is not unique. So we see those in the solar system objects now. So that does not necessitate an artificial explanation for Oumuamua. So it gives us some context. One issue, though, is that these dark comets that we found so far they're still, even though they're stronger non-gravitational accelerations than you typically see on asteroids, they're not quite as strong as you saw on Oumuamua. So one question is, could there possibly be things in the solar system that are accelerating even stronger that we haven't found yet because we haven't connected them? And we miss them when we try to link them up to previous objects, because they've accelerated so much that their orbit changed so much that they're unrecognizable. And that's what me and Jason's recent paper, we're both on Astor Taylor's recent paper, which went into this in greater detail. And I think that's something that's really exciting with the Ruben Observatory coming online. Could you potentially find way more objects that, if you link them up correctly, allowing them to accelerate when you link them up, could you find much stronger accelerations on these dark comets? And then that could even imply that there would be, I'm speculating now, so this isn't a purely scientific statement, but it could be the case that there are a lot more dark comets out there with a lot stronger accelerations than we even realized. And that's kind of touching on the point that Jason made about, once you get up there with the accelerations, you get to the point where you would need a spaceship-like acceleration to make it work.
Yeah, and that's interesting, because you eventually get to the point where it's moving too fast. Its motion is too much to do with volatiles, and that's Techno-signature, right?
Yeah, I think so. Although, that's not the case for Oumuamua, but certainly you get strong enough to at some point, that's got to be what it is. But we don't know what that would look like in terms of not in terms of what the motion would look like. We just don't know if it would even, if you had a acceleration stronger even than Oumuamua's, is it even possible to identify that? I'm not sure that it is.
It may not be that, and that's the problem with a ton of technosignatures is, again, ambiguity.
Right.
You know, it has to be unambiguous before you can sit there and say that's an alien object. There still are only a few ways to do that with any technosignature.
Right.
And that's always going to be a problem. But now that we're thinking about close ones, it's going to be interesting times indeed. And I look forward to the Vera Rubin Observatory and that resolution that thing's going to have. And Darryl, thanks for joining us again. And we'll do this again sometime soon.
Yeah, thanks, John.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.